So now we are going to talk about the work. So a lot of work went into Qt 6 that allowed us to move away from really building exclusively on OpenGL, so being tied to OpenGL. So hopefully some of you have used Qt before. So and of course you might know that in Qt 5, of course, OpenGL was a very important piece because of course we built on that a lot. And of course the world has changed in the meantime. So now we are going to see what happened in Qt 6. So Qt 6 is the current major version of Qt, which is an application and user interface framework, in case someone has not used it before. I should add that, of course, knowing what Qt is, that actually matters quite little for this presentation. What matters more is, it's beneficial if you have some ideas about 3D APIs, such as Vulkan, Metal, Direct 3D, OpenGL, and if you've done some shader programming before, that's even better, because of course that will make it easier to just follow what I'm talking about. But even if not, I think it's still a very interesting thing, because what we have here is a problem which has certain constraints, and then we are going to see basically that what happened, which is basically one possible solution to this problem. And it's not unique, because during the, say, I don't know, last 10 years, I mean, many other projects, so think of game engines, rendering engines, browsers, of course, they ran into something very similar, right? That what do you do in a more fragmented world when you have to deal with multiple 3D APIs and multiple shading languages? So, and of course, what we have here, that's basically one possible answer, I think, how we solved it. And, maybe others have slightly different approaches or solutions. So in that sense, I think it's a very interesting topic. Now, we are not going to spend really much time on what Qt is, but just very quickly. So Qt is many things, but to many people, it's a way, like a library framework, to create user interfaces, well, maybe, cross-platform ones. And of course, the two main ways to do this is, either widgets or Qt unsurprisingly. Now we are only showing complete applications here to show really how simple it is. So there on the left, or you have a CMake project file, and then we have a main CPP, which is a complete portable application. Yeah, what it does, you get a button, which is hopefully a native-looking button, well, depending on the platform, right? This is from Windows, right? So yeah. Now, this is not really interesting to us, because both in Qt 5 and Qt 6, widgets are typically not rendered using accelerated 3D API like OpenGL. Well, it could be, but in most cases it isn't, because how widgets draw, there's the styling, and then it goes through QPainter, which is Qt's imperative drawing API. So yeah, in other ecosystems, so either Skia or Cairo could be similar things, so it's a similar thing to those. And yeah, in most cases it will end up doing the drawing software. What is more relevant to us, because is Qt Quick. Again, a complete application which does the same thing. So CMake project file, main CPP, and now there's a QML file describing a UI, and you get a button, which is even native looking, which I think is a relatively recent feature, right? So that quick controls have a native style. So, it kind of looks like the button looked with widgets. That was not really the case in earlier Qt versions. Okay, this is more relevant to us, because both in Qt 5 and Qt 6, usually anything Qt Quick that actually is rendered through a 3D API, such as in Qt 5 OpenGL and Qt 6, well, some other things. Of course, it should be noted that 3D is of increasing importance. Well, that many people these days want to do user interfaces that combine 2D and 3D. So maybe there are 2D elements, and then it's combined with one or more 3D scenes. And of course, there's more and more talk about 3D in Qt, Qt Quick 3D. Of course, the goal is not to, Qt is now a game engine, because the focus is more on creating these combined 2D, 3D user interfaces, right, which are relevant, in many places. Okay, so that's just an example that if I was to add the View 3D item to the same example after the button, then so then I have a 3D scene. Of course, in there I work with it's a slightly different world now. I work with cameras, lights, models, materials. There's a whole different material system and so on. So it's more like a 3D world there. Or second example, that's just for fun, because it's kind of cool that approximately the same number of lines you can do things like I load up a GLTF model from the GLTF examples repository, and yeah. Or the VAS control, I can move around with keyboard and mouse. So yeah, that's yeah, kind of nice. Okay, but of course I'm also showing this because here it's obvious that something like OpenGL has to be involved, right? So we are not gonna, rasterize and render this ourselves in software. However, even back Qt 5.0, when did it came out? 2012, right? Already then, of course, one of the big new things was, Qt Quick 2. There was a Qt Quick 1 that's not relevant to us. That, it is kind of tied, so, it's always rendered through OpenGL. So that's just a very high-level overview. So, overview that how would a 2D scene like this with a button, red rectangle, text would get rendered. Because of course the story is pretty different from, say, widgets, right? So of course it's not like the rectangle will call draw rect or something from some drawing API. Instead, each of these items like rectangle, text, button will build one or more, nodes in a scene graph. So that's the separate object tree living on the render thread, which was also a fairly new thing in Qt 5. And then there are geometry nodes, transform nodes, clip nodes. Of course, geometry node, what's that? Well, it contains geometry, right? Vertex and index data, and it's associated with a material. And of course, in 2D, what's a material? That's often just a vertex and fragment shader. Okay, so we have that. That's what the Qt Quick renderer works with. And then, it does smart things, maybe merges some geometry together, reduce the number of draw calls, and then it directly goes to OpenGL, right? So of course, there was no separation. Creates buffers, textures, issues, draw calls, GL draw elements. In fact, if I was to take a rendered or capture, that shows very well that was going. That's how it's rendered, right? It's rendered in 3 draw calls, like that was a red rectangle, that part of the button, this presumably a textured quad. And then, that's of course a batching in action. So the 3 text items are merged together. Okay, this is all great, but of course to put it into perspective, of course, using and really building directly on OpenGL was an excellent choice, right? Because, 2009, 10, 11, of course, some of you might remember that Qt was a part of Nokia, and the focus was on mobile phones. And at the time, of course, one of the big things was OpenGL ES 2.0. So the specification for GLES 2, that's from 2008, right? And of course, that was a big thing now that mobile phone hardware will have GPUs that have a GLES 2.0 implementation, which was, of course, a big thing because it had things like you had you had shaders, right? So it was this programmable pipeline instead of the older fixed pipeline. Of course, needless to say, probably of course, Nokia went out of the picture later. But, there is some, quite natural continuation for this story. Of course, partly in the mobile space, so thinking of iOS and Android, but also in embedded devices, which are, of course, pretty important for Qt. And by embedded devices in this context, I mean things like, you have an SoC with a ARM Cortex-A something, ideally paired with a GPU, so not the microcontroller level things. For those, there's a different product like Qt for MCU, which is a quite different thing, although the common part of the story is QML. Anyway, what's relevant here for us, that in that space, of course, there's Linux, Android matters a lot, but there's also others, like operating systems like QNX, Integrity, VxWorks. Some of them are quite important in certain industries, like say QNX and Integrity are very common in automotive, for example, which is important here because these present certain, like constraints, like to what you do with graphics. And of course, during how Qt 5 developed, of course, obviously GLES2 is a fairly limited API for those of you who are familiar with it in its purest form, so without extensions. So of course, optionally, Qt Quick started to take into use a few things here and there. Many of those are actually parts of GLES 3.0, so that spec is from 2012. And but nonetheless, so this dependency on OpenGL worked quite well. And of course, even if you ran a Qt Quick application on your that Windows PC, right? Maybe you had OpenGL, something newer, 3 point something with a lot more features because you had a fancy graphics card and so on. But of course, that doesn't mean that Qt used that, right? Because the main thing in the story, built an OpenGL ES level feature set, and then that's what made things portable. But of course, there is this slight misconception sometimes that OpenGL made things everything nice and easy. So you wrote your renderer once, wrote your shader code once, and it worked everywhere. And well, that was actually not so simple, especially if you're a framework or a library like Qt, which of course valued portability. Not going to dive into too much, but this is to show, and in order to not to romanticize the past too much, that everything was easy when OpenGL was the thing. It was available everywhere, and yeah, it solved all the problems. Because of course there was quite some headache, right, to be able to function with OpenGL ES versus OpenGL, and of course OpenGL evolved. Now you need to deal with the concept of profiles. Like the core profile was the thing where you got the OpenGL context with that, and then the deprecated features are not there anymore. And of course, Qt, people expect Qt is able to function, everywhere. So no matter it's OpenGL ES, a pre-3.2 context, or it's a core profile context. So actually, that's been certain challenges had to be solved during Qt 5. So one quick example is this, that how was the core profile support added or in a way bolted on during this was not even there in Qt 5, this got added later. And of course this is quite telling, right, that all shaders are duplicated, which is of course pretty ridiculous. This could have been solved differently, but of course this is a good enough solution. Again, because on the right you see that the version 150 shader that corresponds to OpenGL 3.2, if you are familiar with GLSL versioning. So that's the one we use for core profile context, because the one on the left may simply be rejected because it's whereas the one on the left is we use everywhere else. Pre-3.2 context, compatibility profile context, or with OpenGL, yes. And then there's another problem there with the precision keywords like this high P, medium P, low P, which again might be rejected with an older OpenGL, like non-ES OpenGL implementation. So of course the story was that we will inject hash-defined blocks and maybe it will be defined out to nothing. Anyway, that's just to show that, yeah, there were some challenges there, which of course Qt had to overcome. But the good news is that it only gets a lot more complicated from here on, because 2014, Metal was announced by Apple, and of course there it was a bit extreme because Apple said OpenGL is deprecated, and everyone will rewrite everything right away because you have the privilege to have an application on that platform. Then you must use Metal from now on, which is okay. Then 2015 you get Direct 3D 12. Well, okay, kind of natural, successor to D3D11. And then February 2016, I think, was when the Vulkan 1.0 spec was published. Now, of course, we don't have really much time to just dive into how these APIs differ from OpenGL. Hopefully some of you have some ideas. But like, for example, how at the time, this whole idea of monolithic pipelines, like big immutable pipeline objects that bake together shader code, state, and a bunch of other things. That was, of course, a very prevalent idea, even though there is some backtracking today. And of course, hopefully, maybe if you did this before, then you have some ideas how this differs, because it can be very different compared to OpenGL, like how you worked with, this so-called OpenGL state machine. Anyway, what matters for us is that there is this fragmentation, right? Because there are we want to deal with all these APIs, because we can't just say that OpenGL it's everywhere. Well, it's kind of going to disappear in the long run. And then what do you do on Apple platforms? Yeah, you want to use Metal. On other platforms, of course, sometimes there are multiple options. That's fine, but ultimately, yeah, we just need to figure something out. So this is a problem statement, like in general, that on top of everything, we had in Qt 5, so all that good portable cross-platform OpenGL support, you now want to enable a lot more, because you also want to be able to function on Vulkan, Metal, and so on. And of course, this applies ideally to the whole of Qt. So Qt Quick, the 3D stuff, and of course Qt Multimedia. So of course, OpenGL was used in a number of places, so this is not just about Qt Quick. But we have constraints. So okay, we have this big existing framework, like the renderers, Qt, and so on everywhere. So of course, you want a solution where the porting works. Of course, it's understood that there's going to be quite some work to move everything over to whatever new solution we will have. But of course, that needs to be something that can be done with a reasonable effort. So we can't really have something totally crazy and low level, so that everything else in Qt will kind of be rewritten from the ground up to support that new abstraction or whatever we will have. Similarly, of course, if you are a Qt user, of course there is this quite strong guarantees for compatibility for the public APIs, public C++ and QML APIs, what application developers use. So of course, the disruptions there should be minimized. And finally, a very important one. So like I said, we want to support every platform, everything what Qt 5 supported, including, embedded, everything. Even though, on some of those platforms, OpenGL ES is and still is the only relevant thing, which of course has the implication that OpenGL, especially OpenGL ES, must still be a first-class target and not an afterthought. So we can't say that, half of Qt will not function there, and then we, I don't know, go out of business or something, right? That would be bad. So the fact that, Qt is used in so many places, that of course presents quite some limitations here. So even today, OpenGL is important. Well, I should say OpenGL ES is important. Okay, now of course, as you can guess, when you have a new thing, new problem to deal with, what is the first thing you often ask, or often what you should ask? In fact, people should ask this a lot more. So how do you avoid solving this problem? Because maybe we shouldn't deal with this problem. And of course, there were like these vague suggestions right over the years. So we're talking about 2017, 18, 19, that, maybe we don't solve this. Let someone else solve this problem. For example, we still continue to use or build on one single thing, be it, let's say, OpenGL or Vulkan, and then we get this, some translation layer comes from somewhere else, and that's, how we will, that's what our story is going to be. So of course, the OpenGL one, that's not really serious. That's just based on this fact that, even Qt 5, I think, for whatever reason, we used to bundle Angle, which that was Google's, at the time, that was an OpenGL ES to direct 3D translator. And of course, based on that, one could say that, well, maybe there will be other similar solutions. So, Qt could just stick with OpenGL. Or the opposite, of course, that was a bit more tempting. But also a bit problematic is that we go all in on Vulkan. It's a shiny new thing. It will be soon everywhere. OpenGL is dead. It's going to disappear. And of course, in the few places where, the platform doesn't or can't have it, then there will be translation layers. Like, of course, Molten VK is the famous example, which the Vulkan implementation for macOS and iOS, where it just does, translates to metal under the hood. Of course, again, this was not really a viable choice because of the slow adoption. If you think of the mobile and embedded space, I mean, Vulkan isn't really replacing OpenGL ES that quickly. So even today, although I'm not going to back this up with data, I think most of the, like say, generally embedded devices built with Qt, so most of those are rendering with an OpenGL ES 3 or 3.1 implementation, which is, of course, quite something, or telling that there's things are moving a bit slow. So of course, it really could have been quite not a good idea to really jump in and build everything directly on Vulkan in Qt. And yes, there could be a lot more. So today you could, of course, ask other things like, why don't you just use this and that? So, the popular question here is that if you are familiar with WebGPU, the successor of WebGL, and how that is implemented in browsers, like for example, Dawn is Google's implementation for Chromium. So, that kind of solves the similar problem, right? That there's a rendering API abstraction, and then it has to work with whatever is underneath, like Vulkan Metal D3D12. And of course, actually, it's a not relatively popular thing to use that, basically take Dawn out of Chromium and use that as your portable C++ rendering API abstraction. Anyway, of course, these are obviously not an option, basically because these things didn't exist 8 years ago, and of course there's a lot more things one would need to think about when once you start using really big third-party dependencies are generally problematic in Qt for various reasons, right? Dependencies involve dependencies. What do you do with all the exotic platforms and so on? So we are actually we do bundle certain third-party libraries, but we need to be careful and somewhat conservative. Okay, of course, it's a bit funny to say that, yeah, third-party dependencies are problematic, and then now let's look at what third-party dependencies we started to use. But of course, there's a difference here, right? Because, things like Spurvy, CrossGL, Slang, these are relatively compact projects, so easy to bundle, they have no dependencies, and so on and so on. So around the mid-2017, so what was prototyped first is the, what do we do for shaders, right? Because that's just, okay, you might have some vague ideas, what do we do, how do we solve the rendering API part of the problem? But actually the first thing that was, maybe the more interesting thing to do first, what do we do with shaders? Because there are different shading languages, right? Metal has a metal shading language, Direct 3D use HLSL, and so on and so on. Okay, so there was this library like Spurvy Cross. I think today that's under the Kronos umbrella. And what does that do? That takes Spurvy, which is an intermediate bytecode format. And that's, by the way, the only thing Vulkan consumes. So, of course, when Vulkan came out, it said that, there will be no equivalent to GL compile shader. Like if you used OpenGL, right, you probably call GL compile shader at some point and you passed in a string. Oh, that was a shader. There is no equivalent, right? With Vulkan, the idea that you write your own compiler or get one from somewhere, no one cares. It's not Vulkan's problem, it's your problem. Or if you are using something like Qt, then it's Qt's problem. Okay, of course, one could argue. Of course, it has pros and cons. So anyway, the only thing there's an intermediate format, right? So that's what you feed into a Vulkan graphics pipeline. Anyway, the nice part is that, Spurvy Cross, that's exactly there to, solve these problems of this fragmented world. So, taking a Spurvy binary, it outputs fairly human-readable HLSL metal shading language or GLSL source code, and actually for GLSL, I can say, or generate this and that version, which of course gonna be quite useful for us later, as we'll see. Okay, can we build on this? Maybe. But what about the first part? And of course, like, probably other projects did this, that was a very popular solution, right? That, you do in the compiler, where do you get one? Of course, many people just use GL Slang, which is a compiler, again, under the Kronos umbrella. Fortunately, not LLVM based, which turns out to be a very good thing because it makes it easy to bundle. There are no further dependencies. So, that's what makes it suitable, basically. So, we can kind of have it in Qt, and So that's what we used to compile Vulkan style GLSL to Spurvy. Of course, there's a catch there that I said Vulkan style, so not OpenGL targeted GLSL, but Vulkan targeted GLSL. So the language is mostly the same, but there are some differences in the semantics. So we compile that to Spurvy, and then the second part is, we use Spurvy Cross to translate to various targets. So we get a Spurvy binary, a number of versions, source versions of the shader in various languages, and a bunch of metadata, which is actually fun, and pack everything together in some data structure. And at runtime, of course, it was envisioned at the time, the rendering API, it will just pick the right one. If it's Direct 3D, pick the HLSL version. If it's Vulkan, use the Spurvy version, and so on and so on. Actually, that was what was prototyped then. Of course, that became a thing, like when Qt 6.0 came out at the end of 2020. That was actually what was started then. That is actually the final solution. So it is building on GL Slang and Spurvy Cross. Just a little bit of insight, like, what Spurvy Cross does, right? Because it's easy to, think, it changes the syntax a bit because shading languages are similar, and the difference is some minor syntax differences, which is not entirely accurate. Because, of course, there are constructs or things that don't map to each other, or different semantics for certain things. And Spurvy Cross does a lot of things, which, of course, other similar solutions may not. So, just two simple examples, like, what would this uniform Exemplar 2D thing, what would this translate to, say, in HLSL? Well, to think much, of course, I can tell you that directly it doesn't map to anything because there is no equivalent. So this is a combined image sampler with Vulkan terminology. So of course, the single binding point, of course, on the API side, you would pass in the texture and the sampler. So, but of course, here on the shader level, it's one thing, which is a bit of a legacy OpenGL thing. But Vulkan support both combined and separate textures and samplers. So of course now, if our translation process would say error not supported, and yeah, it exits, I mean, that would be bad, right? Because then we can't really do this. And of course, we like to do this because this is, how we did things with OpenGL. So of course, now it's pretty much everywhere that you use combined image samplers in shaders in Qt. So fortunately, for example, SperVircus takes care of this because it will output, a separate, like a texture 2D and a sampler state variable. So which of course is more or less the equivalent, but of course in principle, it's not the same thing. And of course, how do we really make sure that things work identically? Because of course now, what is that T0 and S0, right? Those, the whole resource binding model in HLS, it's a bit different. You have these HLS registers and whatnot. How do you know that the SperV Vulkan style binding 1 corresponds to whatever T0 and S0? So of course, this is where, for example, we could have some mapping tables. And of course, this is where I said that there is some metadata. So its story is a bit more complicated than, we feed in our SperV to some translation tool, and then it outputs some shader source, and then that just gets used. Because what it outputs is also a bunch of metadata, which you then have to potentially use when you use that shader. So if we pick the HLSL version of the shader, then we will use that mapping table to know that, when somebody feeds us a texture and a sampler saying binding 1, then this mapping table tells us that, but in this version of the shader, though it actually corresponds to, say, T0 and S0, and so on. So there is a certain So things are a bit intertwined, so there's a coupling between the, this whole shader pipeline and the renderer. Or of course, countless other examples, right? So when you emulate certain things by passing in magic uniforms or buffers, which is of course gets a bit weird sometimes. So, things where SperV cross-generates shader code, which has a, magic uniform or buffer, and then the renderer has to pass some values in there so that the end result is the same. So of course, a classic example, which is a cheeky example because we don't even implement this properly in Qt, that what does GL instance index translate to? So long story short is Vulkan. You can have, if you don't know what the base instance is, so that you can pass in a value to the draw call and think of it that there's an offset. And this variable includes this offset. The equivalent in HLSL, SV instance ID, does not include that offset, so it never includes the base instance. It's always like 0 based, which of course matters if that offset, that base instance was not 0. So of course, what do you do? So of course, SperVircus or whoever implements this has two choices. Well, in very modern HLSL, so latest version, there is a system variable that tells you that base instance value, so you can generate code that, you add this together. It's instance ID plus start instance location. But of course, that will not work with typical HLSL versions we use. So of course, then what does it do? Well, it could generate a magic uniform, add that value, and of course, then whoever uses HLSL shader will now pass in that value there, right? This base instance value. Again, this is just to show that then you have to know about this. So it's that HLSL shader will not be functional if you don't know this and you are not prepared to feed in all that magic extra stuff. Okay, so long story short, this deals with vertex fragment and compute shaders fairly well, very well, I would say. Which is good because that's what we use in Qt. Like this sort geometry and tessellation, well, we partially support that, but we don't use it in Qt. We call Qt 3D, geometry shaders, tessellation shaders. Well, thinking of portability. Like, metal has no geometry shaders, so yeah, that's that. One question currently is that, because this covers, like say, Vulkan D3D11, D3D12, metal, and of course OpenGL, OpenGL, and also WebGL by extension, but what about WebGPU? So one thing that remains to be seen is how and when we support this, because if you've heard of WebGPU, you might know that there is a new shading language. There's a WebGPU shading language, which was introduced for reasons. Of course, the world may or may not have needed a new shading language, but there is one there. And of course, SperVircus does not output this for reasons which are maybe non-technical, maybe political, but yeah, let's not go there. So you can look that up. So of course, that's of course if interested. So for example, here now, well, we'll see what happens. Maybe we bundle, maybe we use another translator. So because the tint would be again Google's shader translator within Dawn. Maybe we could use that. Of course, the goal there, of course, the goal of that is to translate right from WGSL to whatever is underneath, but it also does the opposite, so SPIRV to WGSL, except that it doesn't do a bunch of things. So for example, this example I showed before with this sampler, well, that would just fail because WebGPU does not have combined image samplers, and well, yeah, not supported, end of story. Well, then, so it makes things a bit more complicated. But yeah, we'll figure something out. Okay, so if some of you have used Qt 6 before and worked with, for example, shader effect item there in Qt Quick, then, well, you probably know how this looks in practice. And yeah, don't look at the shader code, it doesn't really matter. So this is just an example from one of the things from the shader effects example that ships is Qt. That, okay, now application developers, well, provide Vulkan style GLSL, which is good because there is a same migration story, right? So it's still GLSL, the meat of the shader is the same, and then there are some differences, usually at the top with inputs, outputs, uniforms. There are no standalone uniforms, there's a uniform block. But the actual porting, so changing, that's usually very straightforward. So this is still turned out to be a very good story compared to, oh, let's use a totally different language. Then of course that's a lot bigger switch to most people if you need to deal with now a fully differentiating language. On the right, yeah, that's the new CMake integration, which is just, yeah, that's cool because you had nothing like that in Qt 5, that, oh, I list my vertex fragment and compute shader source files in a Qt shaders function in CMake, and then magic happens. Things get compiled to SPIRV at build time, and then we do all these other steps. And then back up the resulting artifacts. And, oh, you just use it, right? Fragment shader property of the shader effect, no. Reference is this QSB file, which of course was generated at build time, and it's just there. Magic. And of course, what's inside? Well, inside there are all these things, the SPIRV, HLSL, and various GLSL versions, plus metadata and whatnot. That's all there. And of course, obviously, the renderer will pick the one we need. And of course, this gives us things like build time. There is a syntax error in your shader. No, that's a build time error, which is a huge step forward compared to Qt 5, where you had a warning printed to the debug output at runtime, and who knows where the debug output went. Right, so depending on the platform. And by the way, this also solves that whole GLSL problem I showed for Qt 5 by design, because now you just pick the right GLSL version depending on the OpenGL context you have. Okay, downside, yes, of course, now you don't have, you can't dynamically generate a source string because fragment shader is no longer a string property. It's a file name, well, it's a URL, but yeah, technically. And yeah, of course, it should be noted for correctness that, in the world of 3D, Qt 3D, things are a bit more complicated. So there we still do some things at runtime. So we will do this whole shader compilation, massaging, all that shader processing at runtime, simply because shaders for 3D materials, have to be generated dynamically, which is actually going to be hopefully improved at some point. And if you were into, we were familiar with game engines or somewhat. So of course, this is a bit like this classic shader permutation problem, that if there are so many variations of the shader depending on various settings and the scene, you can have tens of thousands of different shaders. That's, we can't know, though it's not realistic that we know everything and bake everything up front. And of course, whereas for Qt Quick, and the story is so much simpler. So anyway, there is some things to deal with. Okay, but let's move on, because say we have a somewhat decent solutions for shaders. What then? Because step 1 was to figure out how do we deal with the different shading languages. Step 2, how do we deal with the rendering or the rendering APIs? Now, of course, with any big project, it's usually it's very useful if you have some previous, not experience, but if you've done some previous experiments, which then tells you what you want to do or what you not want to do. So for example, in this case, there was actually even 2015-16 or so, which maybe is a little known experiment, or it was part of Qt 5 at some point, and there was a direct 3D 12 backend or renderer for Qt, which turned out to be a very useful thing, not because we used it in any way, that got just thrown away later, but it kind of showed, a possible approach which we do not want to take. So even, in that sense, this can be useful. Because of course that was a Qt renderer, that was a side-by-side, living side-by-side with the main OpenGL-based one, which of course that's not exactly a holistic solution. It doesn't help anyone. Doesn't help Qt 3, doesn't help Qt Multimedia, doesn't help anyone but Qt, and anyway it's bad because we want one renderer, not one for each 3D API. But nonetheless, this then of course shows you very clearly that, well, you want something else. What do you want instead? Well, maybe you want a 3D abstraction on a lower layer. Well, right? So then everything in Qt can use that. So this was, I don't know, started some prototyping or work around 2018. And of course that was started around focusing on Vulkan. Of course that was Vulkan 1.0 at the time. So even Vulkan 1.1 isn't it from 2019? So that was not there. But of course, again, it's important to, maybe understand that given our constraints, what we want is not let's have a nice wrapper for Vulkan, and it will be more C++-ish and more Qt-ish, and it will be beautiful, and that solves our problems, because it's not what you want. You probably want something that does not cover the whole of Vulkan. You need to think of, you still need to support OpenGL and so on, right? Like I said, it's a first-class thing for Qt. And of course, you probably want something higher level in some cases, because again, thinking of that, how will Qt Quick, how will those be ported? I mean, it would be pretty bad if we had a, plain Vulkan style API. It's a bit too low level, right? So, ideally it should have some conveniences while still mapping well to Vulkan and OpenGL and others. So basically what we get is something in between. Maybe with certain compromises and so on. Okay, so this is what I think Qt 6.0 shipped at the end of 2020, and the big thing there was there's something new in the middle, right? So this whole Qt rendering hardware interface, that refers to this class called QRHI and a bunch of related structs and classes is the QRHI prefix. Okay, that shader pipeline that mostly refers to this, what I described before and the associated tooling. And below that, there are the 5 boxes. Of course, at the time that was 4, so the D3D12 that appeared later. The backends for QRHI, right? This OpenGL, D3D11, Vulkan Metal. Of course, the OpenGL one that covers everything Qt 5 covered. So again, this OpenGL, it works in a core profile context, but it works in a compatibility profile context, and so on. Does if this, then, if the context version is this, you can do this, as do that. So of course, it does a lot of those things to ensure, again, the good cross-GL, GLES, and that cross-platform behavior. And of course, on top, now nothing uses OpenGL directly. Like Qt 3D Multimedia, there is no GL whatever, and there are no GLSL source strings sprinkled around. Okay, this was kind of nice and cool, but this was all internal, right? So of course, this was, well, actually, it was not meant to be a fully private API at first, but it was when, initially, really when Qt 6.0 came out. So of course it was meant to be used by Qt itself, not by applications. That actually got a bit relaxed, not so long ago, like in Qt 6.6, that no, the application developers who want to use this, well, can, because there's documentation. Previously, of course, this was completely hidden, right? This QRHI and related classes. Now it's actually there. It's in a bit of a, let's say, semi-public state, right? Because it doesn't come with these full guarantees for binary compatibility. Of course, you're not going to get depointers and whatnot, which then ensure that, so this typical, it's not entirely like a proper Qt API in that regard, because it's just not really reasonable for this. Of course, here some people could start shouting, right, that Qt is now competing with whatever WebGP or insert whatever Vulkan, OpenGL, and why are you doing this not invented here thing? Of course, well, we are doing it because we need it internally in Qt. And of course, the idea is that, to some people, this is useful. Those who actually benefit from this being fully portable, and they find that this API is good enough, good for them. And yeah, there are actually some people at least using this. I'm just basing this on that there is some feedback occasionally, like in our bug tracker and here and there. So I think it gets some use. In any case, this is useful. If for nothing else, then now you can make standalone applications, right? Qt applications which don't just use an undocumented private API, but now use a documented half-private, well, mostly public API. Of course, there are applications like that shipping with Qt, right? Some examples, but I also have a GitHub repository which has 6 Qt applications in a bit more to show this, that, how do we render a rotating triangle, which of course is very common in low-level graphics, that you render a single triangle and then everything works, because that's what you want to see. And yeah, like the first, that doesn't turn a window, that's a console application, right? It renders into a texture, then reads it back and saves it into a PNG image, and of course it generates 20 PNG files. You're not supposed to read that, but this is just to show that does it fit onto one slide? Of course, it's an amateurish screenshot from VS Code with the 3-way split. And yeah, the lines are truncated, but it does fit, sort of. So it's kind of nice that it's less than 145 lines, which is just not unimpressive. Of course, what this does on Windows, it uses D3D11. On Apple, uses Metal. Otherwise, tries Vulkan. If that fails, use OpenGL. And yeah, then you get 20 PNG files. That's not bad for an application of that size because it's fairly portable. Of course, for completeness, there's a CMake project file and the 2 shaders. So, these 4 things together, that's the complete application. It's, yeah, not exactly complicated. So we are going to have a, very basic quick walkthrough, just what you saw on that slide. But of course, the goal is here to not to show really, teach anything from the API. This is to give an impression that, about the structure, basically. Okay, so the first part is probably the least interesting one, that how do we get a QRHI instance? It's not interesting for many, because if you were to use Qt or something, then Qt takes care of this. Of course, this application is, there is no widgets, no Qt, no nothing, so it does everything on its own. Okay, once you have that, what do you render into? You want a texture. Okay, well, we create a texture. What's interesting is, of course, how some of the things, some things from the more modern API shines through, right? That you declare up front that, this texture is going to be used as a render target, or this texture is going to be used as the source in a readback, which, if you work with something like Vulkan, then, well, you know why this is necessary, because a lot of things there need to be known up front. It's then, okay, what's the render target? That depends. Really, because it maps to different things under the hood. Again, there is some weird things with render pass descriptor. Again, you can guess that, well, that's because Vulkan has this concept of render passes and VK render pass, so yeah. Okay, then we will have 2 buffers. We have our vertex data, and there will be a uniform buffer. We'll talk about that later. And then, yeah, binding point 0. If you remember the vertex shader, there was a uniform block there, so that we expose that uniform buffer at binding point 0 to the vertex stage, and then there's a graphics pipeline. Well, that was the setup. Right? These are the things we need to render a triangle. And of course, a pipeline, obviously, this mirrors what you have in Vulkan or modeled, right? This whole monolithic pipeline. It's not very obvious here, but this bakes together so many things, like the shaders, whatever, vertex input layout, other layouts, and all the state. Of course, this just goes with the defaults, right? Depth test is disabled, blending is disabled, but yeah, it's a bit, well, modeled after Vulkan in that regard. Yeah, I'm going to dive this into much. Then we render 20 frames. Get a command buffer somewhere. Again, what that is. Obviously, with OpenGL and D3D11, of course, we have this simulation of command buffers. Not really, there are no native command list concepts in those. Yeah, update the vertex buffer on the first frame. Then, yeah, you push your model view projection matrix on every frame. And then you record the render pass, clearing to green, set that graphics pipeline, draw 3 vertices. And then, yeah, it's quite easy to trigger a readback from that texture and then create a wrapping Q image, because you just use Q image to save to a PNG file. And then, yes. All right, so of course, details of the API where those of you who interested in using this can look into it. I think what's more interesting is look into some patterns. So why did I say that? This is of course a lot higher level. Well, of course, maybe it was obvious from this quick walkthrough than, for example, what you have in Vulkan or D3, D12. Like it's so much more higher level, right? So of course, because we do a lot of things exactly so that the life of Qt, Wix3D, multimedia, and everywhere else is a bit easier. So of course, like if you worked with things like Vulkan, you probably know that the very first thing you learn that you are not supposed to block and wait for completion when you submit a command list. Instead, you are supposed to go on so that your GPU is fed with work and maybe block later, every time when starting a frame, you potentially block, right? If you are too far ahead on the CPU compared to the GPU. And of course, that's what we do too, right? That we try to keep at least 2 frames in flight. But that has interesting consequences for resources. Like what happens to that? Like in the example, that you update this uniform buffer on every frame. And that's a host visible uniform buffer. So basically just map and mem copy data into it. And I said that, what if the previous frame is still on flight on the GPU, so the buffer is used and we are already doing the next frame on the CPU side. And we just mem copy some data to it. I mean, that would be awful. So this is again something that the abstraction deals with internally, that maybe a QRHI buffer is backed by multiple buffers if needed, maybe 2. Maybe there's 2 VK buffers. And of course, it just juggles or swaps between them on every frame. And of course, from your perspective, it's the same buffer, but internally it might actually switch between 2. So that again, of course, it's a, and so on. Or of course, similar things that, can you safely delete a QRHI texture or buffer? Well, of course, you can't if it's used in the frame. You are actually going to, but if it's used in a previous frame and you don't need that anymore, you can. But of course, you know that internally there's going to be a lot of things happening because maybe the native resource, like the VK image, maybe, of course, that cannot just be released if you are not certain that the previous frame, well, it might have been used unless you are certain that that has finished. So maybe it will be deferred. We just put it onto a deferred queue, and maybe it will be freed only when you start a frame later on. And of course, lots of things like how this whole, for example, APIs to do resource updates a buffer, a texture, do readbacks, even generate bitmaps. There is no bitmap generation in Vulkan or D3, D12. So there's a lot of convenience. It's quite high level. And of course, due to this, what I showed in the previous slide here and a bunch of other things, of course, this is when some people, again, could start shouting or yelling, right, that, this is reinventing OpenGL, which is a terrible idea because it's not modern and you have to be low level and you are not using everything you could from Vulkan and so on. But that is partly intentional, right? Given our constraints, we want something that's, there are certain conveniences built in. So, yeah, I think that's actually a good thing. Could talk a lot of other things. How do we deal with OpenGL style data? Like, for example, that NDC, which stands for Normalized Device Coordinates. Of course, this conference, I don't know if it's really named after that. Of course, it's the same problem in clip space. So a vertex shader outputs something in clip space, then you do the perspective divide, divide by the force coordinate, and then you are in that NDC normalized device coordinate space where x and y runs from -1 to 1. And of course, there's an interesting problem there, right? For example, Vulkan 1.0 said that the origin is in the top left corner and y points down, which of course is unlike anything else before in that space, which was kind of a surprise. And of course, there were reasons, weird reasons anyway. And now, you have to, maybe we need to deal with this, right? Because, what we had, the Q matrix 4x4 is a helper class in Qt. For example, that's what we used to get a perspective projection matrix. And in Qt 6, it's identical. Of course, it's built with OpenGL things, conventions in mind. Or similarly, your vertex data everywhere in Qt, or also in this example, is assuming that y points up, right, in the vertices. And then, of course, the front face is counterclockwise by default, the winding order. So, for example, to deal with this, that's why there is this somewhat weird name. There is this correction matrix, which we query from the RHI backend, right? And you pre-multiply the projection or whatever model view projection with that. And of course, with OpenGL, that's an identity matrix. With others, it might do things like flip Y. It also does things for the depths, but I'm not going to dive into that. Really to eliminate these differences, so you think that, oh, everything just works. With the old, so the Qt 5 style content, you can just use that also with Qt 6. Then there's a similar things with images, right? That again, you saw in the example that there it's up to me that if it's OpenGL, use that query, but of course that's in practice a test for OpenGL. If, I might need to flip my image, otherwise my triangle would be upside down compared to the others. Now, of course, there are some, maybe little sad things, because some things were not done, because certain compromises were made. It's the title of the talk, has a lot of joys and sorrows and so on. So, of course, there were things which are postponed or will be investigated in the future. Like, for example, one of the big things in Vulkan D3D12 is that, it's now easy to build command lists on multiple threads, like record, right? So you parallelize, which of course is not necessarily that important. So that's quite a sarcastic sentence there that tries to say that, Qt simple 2D scenes do not benefit from this. But then again, a complex 3D scene might. But again, in the name of keeping the existing patterns and stuff, so this was kind of postponed, right? So we can still, so all these patterns we have in Qt don't break down, that, each quick window has a render thread, each has an OpenGL context, and of course that's the natural continuation. Each quick window has a render thread, each has a QRHI that's only used on that thread, and of course underneath there might be an OpenGL context if it happens to use OpenGL. So again, this is a bit of a compromise. Or there are things which we will eventually need, because we'll need it in 3D, like indirect drawing, but for example, that's not there at the moment, so that's something for the future to be introduced when actually Qt needs it. So this is where, things are kind of driven by what Qt needs, although there are features in there, rendering abstraction, which are, used by some demos, experiments. There were also some contributions from the community. But generally, it has what Qt itself uses. Maybe we'll skip that. And maybe one interesting thing, although it's going to be very trivial, how do we deal with the problem of memory management, right? So with Vulkan, you might know that after you wrote your own compiler, you also write your own malloc. That was the story. Because, so the memory allocation is separated from resource creation, right? So VK create image does not do anything like it. There's a separate VK allocate memory, which of course is supposed to be a slow and heavy operation, and it might have limitations, like, it might not support more than 4K allocations during the lifetime of the application, which is again a thing that, the Vulkan implementation maybe doesn't have to have a general purpose allocator. Maybe it's something simple, and then it's whoever it's the engine's problem to figure out, to allocate big blocks and then sub-allocate. Of course, what do many people do? Go to GitHub, pick AMD's Vulkan memory allocator library, and be done with it. Well, okay, so that's a fairly popular header-only library, right? Which of course does this, so it has these different strategies, allocates big blocks, and then, from your perspective, you have something more convenient. You don't really deal with the problem yourself. Or of course, there's a similar solution for D3D12. Metal is kind of the exception, because that has some of these conveniences built in. So unlike Vulkan and D3D12, unless you use certain features in Metal, it actually has quite a lot of conveniences. So you don't, this whole separated memory allocation is not a thing, and also dealing with barrier synchronization. So actually it has quite a lot of things that which we also build on, which makes the Metal backend simpler. Well, and of course it has instead other problems to deal with. So finally, not gonna really dive into much that how do you get something on screen. Obviously we have to abstract swap chains, like Vulkan swap chains, DXGI swap chains. But if I was to take one of our other examples, which uses QRHI widget, that's a helper class in Qt, and it shows a rotating triangle in a resizable window, and it's portable. So of course the nice thing in this that this can be done, what was it? It's less than 115 lines. Well, you don't read that because the rendering code is mostly the same, which I think is not bad. I mean, it's just a fun thing, right? Because people usually talk about, I wrote a triangle, rendered a triangle with Vulkan in 1,000 lines, but yeah, compared to that, it's not uncool that I can do this in 115 lines. And of course, this works on all those 5 Vulkan Metal, D3, 11, 12, OpenGL APIs. And the window even resizes correctly, which is often overlooked. Yeah, I don't think we will dive much into the, what step 3 was, which is porting Qt and Wix3D to the new abstraction like the QRHI and changing the shaders and everything. The main message, I think, that's what's important. Most of this boils down to a bit of patterns and the structural changes, right? That not really changing GL whatever to something else, but a bit restructuring how you do stuff so that you have well-defined points of preparing resources like buffers and textures, and then you record render passes. Whereas with OpenGL, we had this mess of you could call GL buffer data at any point, right? Or of course, how you deal with monolithic pipelines. The example there on the slide that uses one of the public headers like USG material shader, which maybe it's a good example, because of course, if you used it in your application, well, there we had an API break, right? We can't have a virtual function called update state, which was a very efficient and lean solution for Qt 5, because you could call GL bind texture, GL set uniforms, GL uniform 4FV. You could change state. You wanted your custom blend state, you said that. And obviously this does not map. It's very efficient, but it doesn't map to Qt 6 because we can't have this. Not just because you can't use OpenGL directly, but also the patterns don't map, so you can't just set the blend state when it's part of a immutable monolithic pipeline. So instead, we have 3 virtuals where basically you just tell us what you want, what texture should be used for this binding point, or what should be the blend state, like the graphics pipe, update graphics pipeline. So we give you a struct and you set a few things. And then the renderer takes care of that. So it's kind of, a bit high level. You just describe what you want to do. Whereas in Qt 5, you just directly went to OpenGL and did that, which is a bit funny, but yeah. Okay, so finally, very condensed last slide. What have we learned from this? Well, of course, we learned that fragmentation is annoying, but of course, as we've seen, things were not that simple with OpenGL either. So of course, don't want to romanticize that it was all better than, because some things were simpler. But still, of course, it has to be said that it's a bit unfortunate that now, I don't know, we deal with how many? 5, 6, 3D APIs, and I don't know how many, 4, 3 shading languages. At the same time, I think what we had there, so that we, for the rendering API part, that we directly do, or D3, 11, 12 Vulkan Metal stuff, so don't use translation layers and stuff. I think that is a good and future-proof thing, because we are not limited by some other project or another layer or another abstraction. Right, so we have to do something special. Say we suddenly target, I don't know, do VR, target the Apple Vision Pro. We need to do something special with Metal. We can because we are in control. It's not really abstracted away by some other layer. So yeah, I think this worked out pretty well, even though it's a lot of work now to maintain all that. On the shader side of things, there we do rely on third-party libraries, right? Which of course it could be asked that was this really the good, right choice, instead of, say, inventing something ourselves. I mean, for 15 years at least, people were talking about Qt should have its own shading language, and then we translate ourselves to whatever is needed underneath. I mean, sure, maybe, but again, that has its own problems. And so here, I think it remains to be seen how this scales, because what we have now works very well. Of course, there are some concerns, right? I talked about what do you do with web GPU and so on. So yeah, it remains to be seen. Of course, these APIs are evolving, right? So, yeah, obviously Vulkan is evolving, so that remains to be seen how we follow this in the Vulkan backend, right? I talked about, VK render path shows in the API. It's actually deprecated in Vulkan 1.4 because there's a whole new way to do stuff. Anyway, of course, compatibility is usually pretty good, so it's not like what we have will stop working, but that's something to think about. That how do we follow the evolution of Vulkan Metal, D3D12? And of course, finally, as always, we do have big new abstraction layers and so on. Of course, there were some challenges, right? And there still are some that, you have so much more code, and sometimes people expect things work identically to the old version. Like you move an application from Qt 5 to Qt 6, and yeah, of course, ideally things should work the same, more or less identically, or better. But of course, sometimes, some of the numbers are not entirely the same. So memory usage is higher. Well, of course, nobody said that Qt 6 will allocate the exact same number of memory blocks, right? That's not really a thing we can guarantee. But at the same time, things should be in the same ballpark. Or the same thing with CPU or GPU usage, right? So of course, we saw both that some people said that, oh, things got better. Then some found that, we run the same project with OpenGL also in Qt 6. Maybe CPU usage is a bit higher. Why is that? And yeah, well, there's a lot of new code in there, and sometimes things were not necessarily optimal. So I think a number of things have been really improved over the course of Qt 6, and who knows, maybe there are still some things that can be improved. But all in all, I think it was achieved, right? What we wanted. So yeah, there's Qt everywhere. I think that the tarbos have this Qt everywhere naming, which is pretty cool. So we can say that yeah, this Qt everywhere is still true even in a post-OpenGL world, which was the original what we set out to do. So I think that was kind of achieved. And yeah, things seem to work pretty well. And then yeah, remains to be seen how well things scale in the future. Okay, so I hope this gave some, insight also to what we did, and maybe a little insight to, what some of us work in the Qt graphics team, right? So I think, hope it was interesting to some of you. Yeah, thank you. Of course, we can take those separately afterwards too. So yeah, if you have something.